Watch a drop of ink fall into a glass of still water. For one fleeting instant, it holds together, a single dark bead suspended in perfect clarity. And then, almost immediately, it begins to spread, curling outward in soft, complicated tendrils, until the entire glass is tinted, evenly, gently, with no trace of the original drop remaining at all. I want you to notice something about that moment, something we almost never stop to think about. You have never, not once in your entire life, watched that process happen in reverse. You have never seen a glass of faintly tinted water spontaneously gather itself back into a single concentrated drop. And here is what has occupied a significant part of my career as a physicist. Nothing in the fundamental laws of physics actually forbids that reversal from happening, and yet it never does. Not once, anywhere in the entire observable history of the universe. Today, we are going to find out why time only moves in one direction, forward, relentlessly, without exception. And if you want to keep exploring the deepest, strangest foundations of physics with me, make sure you are subscribed, because the answer reaches all the way back to the very first instant of the universe itself. Let us begin with a simple, honest confession about physics that surprises almost everyone the first time they hear it. At the level of individual atoms, of single collisions between particles, the laws of motion do not care which direction time runs. Reverse the motion of every single atom in that spreading ink precisely, perfectly, and the mathematics says they would spiral back together into a single drop without breaking a single physical law. The individual rules of the universe are, in a very real sense, blind to the difference between yesterday and tomorrow. So the answer to why time only moves forward cannot come from the individual rules alone. It has to come from something else, something that only appears once you stop looking at one atom and start looking at trillions of them together. Let me make this even more concrete, because I think it is worth really sitting with. Picture two billiard balls colliding cleanly on a table, one striking the other, sending it rolling off at a precise, calculable angle. Film that collision and play the film backward. The reversed collision looks completely plausible, completely normal, obeying every single law of motion exactly as well as the original footage did. Newton's equations, and even Einstein's equations after him, genuinely cannot tell the two versions apart. If the entire universe were built from nothing but a handful of billiard balls colliding in empty space, there would be no meaningful difference between yesterday and tomorrow at all. But the moment you introduce enough particles, enough atoms, enough genuine complexity, something changes, not in the underlying rules themselves, but in what those rules make overwhelmingly likely to happen. This is precisely why physicists needed an entirely new branch of physics to explain it, something beyond Newton's clean, deterministic clockwork universe. They needed statistics. They needed probability itself, applied not to a handful of billiard balls, but to numbers so large they become difficult to even meaningfully picture. Numbers like the roughly 10 to the 25th power molecules of air quietly moving around inside the room you are sitting in right now. Picture a single delicate house of cards, painstakingly built, level by level, until it stands there, fragile and improbable, in the middle of a room. Now picture a gentle breeze passing through that same room. There is exactly one way out of an almost uncountable number of possible arrangements for those cards to remain standing as that careful, ordered structure. And there are millions upon millions of ways for them to end up scattered, collapsed, disordered across the floor. The breeze does not know anything about houses or cards. It simply nudges the system toward whichever outcome is overwhelmingly, statistically, more likely. And nearly every possible outcome looks like collapse. This is the deep secret hiding inside what physicists call entropy, and inside the man who first truly understood it, a 19th century physicist named Ludwig Boltzmann. Boltzmann realized that disorder is not simply more common than order by chance. It is staggeringly, overwhelmingly more common, because there are so many more ways for a system to be disordered than there are for it to be precisely, carefully arranged. Time does not move forward because some law commands it to. Time moves forward because the universe, made of an almost incomprehensible number of individual particles, is constantly, relentlessly drifting from the very few possible ordered arrangements toward the vastly larger sea of disordered ones. This single idea, once you really absorb it, explains an enormous amount about the world around you. It explains why the ink spreads but never regathers. It explains why that shattered teacup from an earlier moment in your own life never reassembles itself. It explains why houses crumble into ruins over centuries, but ruins never spontaneously rebuild themselves into houses. Every one of these is simply entropy, quietly, patiently doing what entropy always does, nudging enormous systems of particles from rare, ordered arrangements toward the far more common condition of disorder. But here is where the story gets genuinely uncomfortable, and where I think most explanations of this topic stop just a little too early. If disorder is simply more common, more probable, then the universe, at every single moment throughout its entire history, should have already drifted toward maximum disorder long ago. So why does our early universe, the universe closest to the Big Bang, appear to have started in a state of almost impossibly, exquisitely low entropy, a state so ordered, so improbable, that physicist Roger Penrose has calculated the odds against it as one of the strangest numbers in all of physics? A number so vast that writing it out in full would require more digits than there are particles in the observable universe. Let me try to give that improbability an actual number, because I think abstract words like rare and unlikely lose their weight without one. Physicist Roger Penrose calculated the odds against our universe beginning in a state this precisely ordered by pure chance, and arrived at a figure so large that if you wrote a single zero on every particle in the observable universe, filling each one completely, you would still fall unimaginably short of writing out the full number. This is not simply unlikely the way winning a lottery is unlikely. It is unlikely on a scale that makes every lottery ever played, every coin ever flipped, every shuffled deck of cards in human history look like a foregone conclusion by comparison. Picture discovering an enormous, elaborate sandcastle, standing perfectly formed on an empty beach with no footprints leading up to it, no sign of anyone having built it at all. You would immediately, instinctively want to know how something so ordered, so improbable, simply came to exist that way from the very beginning. This is precisely the mystery sitting at the very start of our universe. Physicists call it the past hypothesis, the simple, unproven assumption that our universe began in an extraordinarily low entropy state, and that this singular fact, more than any law of physics itself, is the true hidden origin of why time flows forward at all. We do not yet have a complete, settled explanation for why the universe began this way. I wanted to be honest with you about that. It remains one of the genuinely open, unresolved questions sitting at the very foundation of cosmology. But whatever the reason turns out to be, everything that has happened since, every spreading drop of ink, every crumbling wall, every year that has ever passed, has simply been the universe slowly, patiently unwinding from that single, improbable, orderly beginning. And that raises a question I think is even stranger than the ink, or the sandcastle, or the shattered teacup. If entropy explains why physical systems drift toward disorder, does it also explain something far closer to home? Does it explain why you remember yesterday but not tomorrow? Does it explain the very sensation of being a person, moving steadily forward through your own life? That is exactly where we are headed next. Stay with me. We discovered that entropy, the steady drift from rare, ordered arrangements toward vastly more common, disordered ones, is the true engine behind time's forward direction, and that this entire process appears to trace back to an almost impossibly ordered beginning at the birth of our universe. But I left you with a question that reaches far closer to home than ink drops or sandcastles. Does entropy explain why you remember yesterday, but never tomorrow? The answer, remarkably, is yes, and I think it is one of the most beautiful, underappreciated ideas in all of physics. Consider what a memory actually is physically. It is not some mysterious separate substance. It is a specific, ordered arrangement of connections inside your brain, formed the moment something happens to you. Creating that ordered arrangement, like building any ordered structure at all, requires the same kind of entropy-increasing process we talked about in the first part of this journey. Forming a memory releases a small amount of heat, a tiny puff of disorder pushed out into the surrounding world, in exact accordance with the same statistical current that spreads ink through water and crumbles houses into ruins. This means memory itself can only ever point in the same direction entropy points. You cannot form a genuine memory of tomorrow, not because some mysterious barrier prevents it, but because doing so would require entropy to spontaneously decrease, the ink gathering itself back into a drop, the shattered cup reassembling in your hand. Your own memory, the very thing that makes you feel like a continuous person moving through time, is quietly, invisibly riding the exact same current that governs every collapsing sandcastle in the universe. I want to pause here and address an objection that troubled physicists themselves for decades, because I think it deepens the whole picture rather than complicating it. A contemporary of Boltzmann's, physicist Joseph Loschmidt, pointed out something seemingly devastating. If the underlying laws of motion are genuinely reversible, as we established at the very start of this journey, then for every single sequence of events that increases entropy, there must exist an equally valid, equally lawful sequence that decreases it, simply by reversing the velocity of every particle involved. Boltzmann's answer, refined over years of careful argument, was not that such reversals are impossible. It was that they are so staggeringly improbable, requiring such an exact, coordinated reversal of an almost incomprehensible number of individual particles, that we should never expect to witness one in the entire lifetime of the universe. The laws permit it. Reality and practice simply never rolls those particular dice. Picture walking across a stretch of freshly fallen snow. Behind you, a clear, unmistakable trail of footprints, each one telling a precise story of exactly where you have been. Ahead of you, smooth, undisturbed snow, holding no trace of where you are going next. This is not because the future does not exist. It is because only the past leaves footprints behind. Only the past has already undergone the entropy increasing process required to leave any trace at all. Physicists call this the psychological arrow of time, and remarkably, it turns out to be nothing more than the same thermodynamic arrow we discovered in the first part of this journey, simply reflected inside the delicate architecture of a living brain. This connection runs even deeper than I have described so far, and I want to walk you through something that genuinely unsettled physicists when they first fully understood it. If entropy explains both the physical direction of time and our own psychological sense of moving through it, then in any conceivable universe capable of containing something like a conscious mind, that mind would always experience time as flowing away from lower entropy and toward higher entropy, regardless of which actual direction, if any, the universe's true external clock happened to be running. In other words, even if you somehow found yourself living during a hypothetical future era when the universe's overall entropy was decreasing, you would not experience it as living backward. Your memories, your sense of a personal past, would still point toward whatever direction entropy was increasing for you locally. You would simply call that direction forward, exactly as we do now. This leads physicists to a genuinely strange thought experiment, one that has caused real, serious unease among cosmologists, called the Boltzmann brain problem. If entropy inevitably increases across a large enough span of time, and if the universe continues forever, then extremely rare, random fluctuations could, in principle, briefly assemble a fully formed conscious brain, complete with false memories of an entire lifetime that never actually happened, out of pure disordered chaos, purely by chance. The same way it is not mathematically impossible, only staggeringly unlikely, for a scattered pile of parts to spontaneously assemble into a working watch. Picture standing in front of an enormous vault, filled with an almost infinite number of scrambled jigsaw puzzles, tumbling and shifting forever. Somewhere at some unimaginably distant moment, mathematics tells us a handful of pieces could, purely by chance, briefly click into a small, coherent picture before scattering apart again. Cosmologists take this strange possibility seriously enough that it actually factors into serious debates about which models of our universe's long-term future are more or less likely to be correct. Precisely because a healthy theory of cosmology should not predict that most conscious observers are simply random statistical flukes rather than beings like us, who arose through the ordinary patient unfolding of stars, our planets, and evolution. There's one more piece of this puzzle I think deserves real attention because it comes from one of the strangest corners of physics I have ever studied. In the 1970s, physicist Jacob Bekenstein, followed shortly after by Stephen Hawking, discovered something nobody expected, that black holes themselves carry entropy, an almost unimaginable amount of it, proportional not to their volume, but strangely to the surface area of their event horizon. A black hole, it turns out, is not simply a void of nothingness. It is, by a wide margin, the single most disordered object we know of anywhere in the universe. Picture the entire universe as an enormous patient furnace, slowly, quietly converting every ordered structure within it, every star, every galaxy, every civilization that ever rises and falls into something progressively less ordered, progressively more spread out. Black holes sit at the very end of that furnace's work, swallowing whatever ordered matter falls into them, and converting it into the most profoundly disordered entropy the universe is capable of producing. Some cosmologists now believe that in the almost incomprehensibly distant future, long after every star has burned out, the growth and eventual evaporation of black holes may represent nearly the final chapter of entropy's long, patient story, the last significant increase in disorder before the universe finally settles into a cold, silent, maximum entropy stillness. Physicists call heat death, a state so uniform, so evenly spread that no meaningful change and therefore no meaningful time would have anywhere left to go. I do not want to leave you with a purely unsettling image, because underneath all of this strangeness sits something I find genuinely moving. That single, improbable low entropy beginning at the birth of our universe was not simply a random accident happening to nobody in particular. It was, in a very real sense, the beginning of every footprint, every memory, every drop of ink that has ever spread through a glass of water, every single moment you have ever lived, all of it flowing directly, unbroken, from that one extraordinarily rare, extraordinarily precious starting condition. So where does this leave us at the end of our journey together? Time moves forward not because the universe demands it through some rigid, unbending law, but because we happen to live inside an unimaginably vast statistical process, one that began in a state so improbably ordered that physicists still do not fully understand why, and that has been patiently, quietly unwinding ever since, carrying with it every memory you have ever formed, every person you have ever loved, every version of yourself you have ever been. That drop of ink spreading through the water at the very beginning of this journey is not simply a curiosity of physics. It is, in its own small, quiet way, exactly what is happening inside you right now as you listen to these words, as this exact moment becomes a memory, joining the long, unbroken trail of footprints stretching out behind you. Exploring the deep, honest architecture hiding beneath our everyday experience is exactly why I do this work, and exactly why I wanted to walk through this particular mystery with you. If this changed the way you think about your own memories, your own footprints in the snow, then make sure you are subscribed so we can keep exploring these questions together. Tell me in the comments, now that you understand where the arrow of time actually comes from, does it make the passing of each day feel more precious to you, or simply stranger? Until next time, keep looking up and keep asking what is quietly unwinding behind you.